Well, maybe we'll kick things off. Hey, good morning, good evening, good afternoon to everybody attending. A real pleasure today to welcome Dr. Branko Damjanac. And Branko is a principal engineer at Itasca Consulting Group. He earned a PhD in civil engineering from the University of Minnesota, and his expertise is in geomechanics and modeling coupled processes in geomaterials. And so for over 35 years, he's provided consulting services to various industries, and these have included mining, nuclear waste disposal, petroleum, civil, and geothermal. And some examples of projects that he has worked on or has been member of teams include looking at mechanical effects of underground nuclear explosions, long-term geomechanical performance of excavation for nuclear waste disposal, stability of underground and open pit mines, as well as hydraulic fracturing for petroleum, geothermal, and mining applications. So a real pleasure to introduce Dr. Damjanac.
Uh, Thank you, John. Uh, Good morning, everybody. Thank you for joining the seminar. Today, I'll be talking about modeling of hydraulic fracture initiation and propagation at Utah Forge, with particular emphasis on the effect of pre-existing fracturing. I'd like to mention that Hafsa Townsy and Wei Fu actually did all of the work and generated the result that I'm going to use in the presentation today. I'm pretty certain that most of you know about Forge. I'll just remind you that Forge stands for Field Observation Observatory for Research in Geothermal Energy. It's a DOE-funded project. It's a field operation in near Milford, Utah, managed by Energy Geoscience Institute of University of Utah. So here you see the aerial view of the Forge site with numerous wells, including observation and site characterization wells. But then there are also two wells which are designed to be injection, which is 16A well, and production well, which is 16B. 16A is also used for the reservoir stimulation. So 16A well was drilled first, and the well is vertical to a depth of approximately 500 feet, where it actually kicks off as a highly deviated at 65 degrees, and then extends to approximately depth of 10,000 feet. The first three stages at the toe 16A well were stimulated, and mainly the microseismic data during stimulation of these three stages, and also based on some modeling results, it was decided that the production well should be drilled approximately 100 meters above. After the production well 16B was drilled, some circulation tests were carried out that confirmed connectivity between these two wells. However, it was assessed that the permeability that was established by stimulation was not insufficient. For that reason, the second phase of stimulation, which included 7 stages carried out in 2024, was done using commercial scale hydraulic stimulation using relatively large injection rates up to 80 barrels per minute and large volumes. During the stimulation of those 4 stages, the reservoirs was carefully monitored using fiber optic and microseismicity, and those monitoring data indicated relatively complex induced fracture geometries and complex interaction of the fractures and apparent pre-existing natural fractures. So one of the objectives of the results of the work that I'm presenting today was to use numerical models to investigate, the effects or stimulation of the reservoir during those 7 stages, and to investigate how the pre-existing fracturing of the reservoir affected this stimulation. The other observation during fracture propagation, but also during subsequent circulation tests, was that the injection pressures, although less than during circulation for stages 1 to 3, were still relatively large, which indicate apparent near-wellbore tortuosity and relatively large pressure drop. So for that reason, another set of modeling was carried out to investigate near-wellbore tortuosity and associated pressure drop. So here is another view of the forged site, also showing the geometry of the well 16A and 16B, and also details of the 7 stages. So there are stages from 4 through 10. Stages 4, 5, and 6 had 1 cluster per stage. 4, 7 included 4 clusters per stage. 8 and 9 had 8 clusters, and stage 10 again only 1. So for this modeling exercise, we used the numerical modeling tool that was capable to simulate treatment of the rock mass by fluid injection, considering rock mass as a naturally fractured medium. So the numerical code that we use, XSite, represents rock mass using synthetic rock mass approach, or SRM approach. So the essence of the SRM is that it's a mechanics-based model of naturally fractured rock mass, capable of simulating fracturing of the intact rock, but then also response of pre-existing fractures by potential slip and opening. And in XSite, the SRM is implemented using a lattice model, and the simple sketch of cartoon illustrating lattice is shown on the right. So basically, it's quasi a random array of nodes connected by elastic springs, and those springs can break. I just want to point out that cartoon shows only 1 spring connecting 2 nodes, but in reality there are 2, because there is another spring which also generates forces due to shear displacement between the nodes. And in XSite, we implement fully coupled hydromechanical behavior. So discrete fractures are represented as a network of the pipes connecting fluid elements created at the locations of the broken springs, and the permeability of these fractures depends on apertures, and apertures or the formation of the matrix results in aperture change. The pressure inside the fractures affects both strength and the deformation of the fractures and the surrounding matrix, and then also the deformation of the solid can cause changes in pore pressure under undrained conditions. And the code was tested, verified, and different functionalities were validated. So specifically for the hydraulic fracturing, the code was verified both for viscosity and toughness dominated regime. In this project, particularly in the near-wellbore model, we also look at the effect of thermal effect on the effect of cold fluid inside the well, and the capability to simulate heat conduction in the rock, which is again coupled with mechanical strains and associated deformation and stress changes. So the heat conduction model is verified and validated as well, as shown here. So first, I'm going to talk about near-wellbore modeling. So why is the near-wellbore tortuosity important? Well, because it does affect during stimulation, it affects the treating pressure. It also affects the proppant transport, potential bridging, and the screen out. And then during production, which is particularly important for EGS, it affects the fluid circulation pressure, directly affecting the economics of the operation. So what are the challenges of modeling near-wellbore fracturing behavior? Well, the model needs to deal with multiple different length scales. It requires detailed representation of the well and the perforation tunnels, representation of different structures, cement, casing, and then how those interact with the surrounding rock. Also, the model needs to be able or be capable of simulating very general complex fracture geometry and interaction of different fractures initiated from the perforation tunnels. And the whole process is actually governed by stress changes from in situ far field stresses to perturbed stresses around the well, and then also stresses perturbed around the perforations. And as I mentioned, there are also the potential thermal effects. So in the case of the stages 4 through 10 at Forge, what has been observed, and here I showed some data recorded during the stimulation, the injection rates, the concentration, proppant concentrations, but then also the surface pressures. Now, using the surface pressures, the bottomhole pressures were calculated, and keeping in mind that minimum in situ stress at the depth of these stages around 6,000 feet, we see that the net pressure is between 2,000 and 4,000 feet, which is quite large net pressure during the fracture initiation. So based on these data, it appears that there is significant effect of the near-wellbore tortuosity. So one of the objectives of the models were to basically understand what is the affecting that wellbore tortuosity. Is it maybe the fact that the well is dipping at 25 degrees instead of being perfectly horizontal, or there is some issue of the interaction of these different structures, cement, casing, or there is some issue with design of the perforations. And here is actually detail of the model geometry, which closely replicates the actual geometry of the perforation cluster. So the model since we are dealing with near-wellbore conditions, dimensions are is basically cube, 6 meters edge length. So the model is basically focused on the detail of the well and that particular stage. In the model, the well appears vertical, but the in situ stresses are rotated to correctly represent the actual conditions that would exist at the geometry of the well, which is at deviated at 65 degrees. So the perforated section is 6 feet long, and there are the perforation design has 6 shots per foot phased at 30 degrees with a total of 36 perforations, and all of those 36 are included in the model. The 7-inch casing is used with borehole with the diameter of 8.75 inches. So here the properties, in situ conditions in terms of stresses, pore pressures, and then properties of different materials, the rock mass, we use the realistic properties for cement and the casing. So I'd like to mention that in this particular model, we didn't simulate the leak off. We believe that simulation time was so short that leak off is probably not important. We didn't include natural fractures, thermal advection in the fluid, nor heat transfer between rock and the fluid. So on the left side, I show again the recorded rates and the pressures, including the bottom hole pressure. The peak or breakout pressure appears to be 68 megapascal. I want to mention that there is slight uncertainty in the calculation of the bottom hole pressure because of the estimation of the frictional losses and so on. So for that reason, when we compare the results, and the numerical result is shown on the right side, which is black line, we also showed actually 2 lines. One where we don't actually, the bottom hole pressure calculated assuming that there is no frictional losses, and then the bottom hole pressure based on estimation of those losses. And what we see is that the model actually fairly well predicts this breakout pressure. Just keep in mind that the time scale is very short. So basically, again, both lengths and the time are very short. So we focus on just the fracture initiation or the breakout. Now, when we look at the geometry of the model and induced micro cracks at very early stages during injection, and the time in terms of, or the state of the model, considering the injection pressure history recorded in the model, is indicated by this vertical red line. So so we show the results in 2 views. One is cross-sectional view. One is the basically lateral view in the direction of the major horizontal principal stress. And at this early stage, and then also there is zoom in. So there are a few interesting observations here. One is basically that actually there is a lot of cracking. So the gray dots actually represent cement, and the yellow are the casing. There's no color for the rock. So the one observation is that there is actually significant cracking of the cement, and as you will see later on, this seems to have also effect on a near-wellbore tortuosity. So basically, what we see is that there are these hydraulic fractures initiated from these multiple perforations, but then there is also significant cracking in the cement. At the later stage, which is basically end of the simulation, the geometry of the induced fractures is shown on the right side. So there's this a view, rotating view showing fractures from different directions. And then there is a plot. So this view also shows the contours of the aperture. Then there is also a plot of at the same state of the fracture geometry, but then the different colors actually shows the micro cracks induced from different perforations. So observation from this is that as the injection continues and the micro cracking develops, there is actually first one micro, basically they coalesce initially along the well. And that is actually perpendicular to far field maximum compressive stress. However, the stress concentration and perturbation by the well actually makes that favorable direction. So there is a fracture going along the well. But then at the end of the perforated section, the fractures start turning. So those are these wings, basically in the direction parallel to SH mean. Now, on the left side, this is just qualitative comparison. There is a plot from a paper on the lab experiment of the fracture geometry, and the resemblance between these two geometries we believe is quite remarkable. So then, in addition, we actually looked at basically what is the perforation efficiency, or how is the fluid distributed between different perforations. So we can, looking at that plot of the microcracks connecting to different perforations, we can actually calculate the area. And basically what we see is that there is very non-uniform distribution of the fluid between different perforations, and that the perforation efficiency is quite low, between 10 and 20%. And in the end, here we show just those fractures with perforations that take the largest volume of injected fluid, and basically those are the fractures that eventually connect to the coalesced fracture oriented in the direction of the minimum far field stress. So then we did some additional analysis where we look at the effect of cement quality and also the effect of DFN on the fracture initiation. So the geometry of the DFN included in the model is kind of shown as these transparent polygons on the left side. And in this analysis, we assume that the DFN is basically frictional in situ permeable, and these fractures in terms of sizes range between 0.6 and 10 meters, and the geometry is based on FMI logs and the study carried out at the Ford project. So here I show the results. First, on the left side is injection net pressure, bottom hole pressure as a function of time for case without DFN and with DFN. In both cases, we consider cement as infinitely strong, so we prevent fracturing of cement. So one observation is that with very strong cement, we don't have the near-wellbore tortuosity that we observed when we consider realistic strength of the cement. And what we see here is that there is one fracture which, okay, initially there are multiple fractures initiated from different perforations, but eventually they coalesce in a single fracture perpendicular to far field SH mean. If in the same model we include DFN, the geometry is more complex. Actually, we see that there are like two fractures or where the injected fluid localizes. There is first one that is initiated first, but then later on another fracture is initiated, and the fracture eventually from the actually pre-existing fracture basically reinitiates in the direction of the minimum horizontal principal stress. And I'll show you in the next couple of slides how these fractures evolve, and the location or the state of the pressure at each snapshot is shown indicated in the chart on the left side. So the state A is basically after the initial breakout, the pressure drops, and basically what's happening is the fractures start propagating perpendicular to far field stress. But then at one point, it intersects the pre-existing fracture, which arrests its propagation and forces reopening of that pre-existing fracture, which is not oriented in optimum condition, in optimal way relative to far field principal stress, resulting in increase in the injection pressure. So then in the next state, that increase in pressure then basically reopens another pre-existing fractures at certain angle relative to the far field principal stress. And then eventually the hydraulic fracture through the intact rock oriented in direction of the minimum horizontal principal stress reinitiates from that pre-existing joint. Okay, so the next step or second set of modeling was carried out looking at response of the reservoir to stimulation, but looking at the reservoir scale. So here are a few more details about these stages, and you saw already the geometry of the stages. Here in this table, we also provide additional information. So stages, stage 4 used the slick water, stage 5 and 8 used the cross-linked fluid, and then slick water was used again in the stages 9 and 10. And then we see that these two stages that had 8 perforation clusters were stimulated at 80 barrels per minute, while the other stages were stimulated at the maximum pumping rate at 35 barrels per minute. We analyzed these 5 stages. So stages 6 and 7 were not analyzed because the results were not very clear, and they kind of indicated as if there was no hydraulic fracture actually initiated or propagated from those stages. So the reason why we are quite interested in and why we carried out this modeling of hydraulic fracture propagation on a reservoir scale are the basically observations from fiber optic monitoring, which indicate that these fractures did not propagate in a way that we would typically expect based on experience from, let's say, shale gas operations, where given certain cluster efficiency, we would have, number of fractures propagating more or less perpendicular to the minimum horizontal principal stress. Here, these fiber optic data indicate the different corridors. So basically, here is indicated how the stimulation from different stages resulted in strains or connectivity in well 16B, suggesting that there is much more complex fracture geometry or reservoir response than what you would expect based on previous experience, and also suggesting that there must be some effect of pre-existing DFN on the reservoir stimulation. So in this model, now we totally abstract the near-wellbore condition. So this model really doesn't deal with near-wellbore fracture tortuosity, nor is capable of predicting early time pressure responses. So basically, we assume that in these models that the fracture has already been initiated and that it took the orientation which is perpendicular to far field minimum principal stress. From that point on, then this model is used to simulate the fracture propagation. And as you can see here, the near-wellbore model is cube with 6-meter edge length. This model is again cube, but with 600 meters edge length. And the rock properties and the operational data and in situ conditions are same as in the near-wellbore model. However, in this model, we include discrete fracture network with almost 18,000 fractures. It is predominantly stochastically generated DFN with some deterministic component based on microseismic data from stimulation in 2022. And the DFN includes fractures in sizes ranging from 10 to 150 meters. Some preliminary assumptions that the fracture apertures range from 0.1 to 0.6 meter, which to me, for unstimulated DFN, seems to be relatively large values of the aperture. And as you can see, the modeling indicates that smaller apertures actually fit better the field data. The most uncertain parameters in this study are hydromechanical properties of the DFN. I mean, what is the, as I mentioned, what are the hydraulic apertures of the fractures? Are they actually permeable in situ or not? And then what are the mechanical properties, the strength, cohesion, and so on? I mean, there has been lab testing of the rock and the fractures, but there's still uncertainty, and particularly in a sense how these behave in situ. So we did carry out a simulation where we assumed that friction angle for all DFN fractures is 37 degrees. But then we carried out analysis where we assumed that the DFN is only frictional and in situ permeable. Then the other scenario is that the fractures have cohesive and tensile strength, 20 MPa and 10 MPa. But then for that scenario, we also looked at condition where although the fractures have this cohesive and tensile strength, they are in situ permeable, but then also a scenario when they are in situ impermeable. And then finally, we also look at the sensitivity with respect to this initial hydraulic aperture or the permeability. So we carried out, actually we did two models. So in one model, we look at only stages 4 and 5, and then in the other model, we look at the stages 8, 9, and 10. And including multiple stages in the same model is important to basically take into account of the stress shadow effect. So here are the results of the numerical modeling compared with the field data. And again, these black thick lines are estimated effective downhole pressures, and then model results are these yellow, blue lines, kind of thin lines. And these multiple results correspond to these different scenarios or sensitivities in terms of hydromechanical properties of the DFN. Okay, one thing I want to point out. So, as I said, the model doesn't this model doesn't simulate fracture initiation, breakout pressure, and so on. Then there is this transitional period where we believe that there is some effect of maybe erosion, basically evolution of the conditions in a near field that affect this near field pressure drop. So the model also, this model is not also capable of basically, it doesn't include these effects. So basically, our target is to match these far field pressures when basically the effective pressures more or less stabilize. So keeping that in mind, basically what we observe is that the model where we assume that the DFN is impermeable actually matches the field data for stages 4 and 5 the best. The case where we assume that DFN is fully permeable frictional underestimates the injection pressure. Now, if you look at the modeling results and we look at them for stages 4 and 5, and actually there are two sets of results included here. So the upper plots are actually showing, so these transparent polygons are pre-existing fractures. So one thing that's important to know is that I mentioned the stages, first 3 stages. Actually, the third stage seems to have propagated hydraulic fracture, basically perpendicular, more or less planar, perpendicular to SH min. So that's this large polygon, transparent polygon here. And that fracture from stage 3 is quite close to stages 4 and 5. So the purple dots are actually micro cracks predicted in these models for stages 4 and 5 for the case where there is impermeable cohesive DFN. So basically what we see is that there is some fracture propagation through the intact rock. Then that fracture gets arrested and completely diverted into the pre-existing fracture or hydraulic fracture created by stage 3. Now, if you look at the two bottom plots, those are actually contours of the aperture. And what we see is that, so basically this outline here, that's that pre-existing hydraulic fracture created in stage 3, that actually stages 4 and 5 actually just get diverted into that fracture and then just keep inflating it. The similar results for the case when we assume that the fractures, pre-existing fractures actually have lower in situ aperture, hydraulic aperture, gives us similar results, but actually more fracturing through the intact rock. So these are results for stages 4 and 5. And now we differentiate microcracks induced by these two stages by different colors. So basically what we see is that first there is a fracture created by stage 4, then some additional cracking due to stage 5. But again, the mechanism is quite similar. That basically that fracture gets arrested and completely diverted into the fracture created by in stage 3. So this is again, this is a cartoon or schematic interpretation, but we see that this response obtained in a model actually fairly well matches the interpretation of fiber optic data. Now, if you look at the comparison of the model results with the pressures for the stages 8, 9, and 10, we see again similar trend that actually the case with impermeable cohesive DFN and particularly with reduced initial aperture actually matches pressure quite well, especially in cases 8 and 10. There is some mismatch in stage 9, and where for some reason the assumption or scenario when the DFN is frictional in situ permeable actually matches pressure better, but we believe that there is some effect of local conditions in this case, or maybe some error or uncertainty in the calculation of bottom hole pressure, because even if you compare the net pressure for stage 9 with those for stages 8 and 10, we see that they are significantly lower. So here we have 80 megapascal, while here for some reason it's 50. Now, if you look at the model results in terms of induced micro cracks and the pressure, what we see is again that case with impermeable cohesive DFN, and on the top actually we show the induced micro cracks. Different colors correspond to different clusters. We see the response where the stimulation is combination of the propagation of the fracture through the intact rock, which are these dots, which then basically also get diverted into the pre-existing joints, which also open, which we can see there here in the plot of the apertures. On the other hand, if we compare the case where we assume that DFN is frictional and in situ permeable, it's purely DFN response. So these dots basically appear just at the boundaries of the pre-existing fractures that have been reactivated, but the fracture doesn't propagate far. And if you look at the contours of the apertures, we see that under this assumption, we are basically just inflating DFN, and we are getting completely different response, which is not consistent with the field data and observation. So when we compare or look at the results for different stages, 8, 9, and 10, we basically see that for stage 8, we generate two primary flow paths, and again, which are a combination of intact rock fracturing and reactivation of pre-existing joints. But we also see the trend, which is similar what we see from the fiber optic data, that the fractures or the stimulated domain is shifting westwards or in the direction of the heel of the well. Stage 9, it basically does additional extension of these flow paths westward, and stage 10 is just basically continue inflating or stimulating the same fractures created in stages 8 and 9. So in summary, the near-wellbore model shows that early time fracture propagation happens both in a cement and rock matrix. The model predicts breakdown pressure that agrees well with the field data, and it also indicates relatively low perforation efficiency. So the near-wellbore tortuosity and low perforation efficiency seem to both result in a relatively large near-wellbore pressure drop. I didn't show the results for the case of a horizontal well. that doesn't seem to reduce this effect of high near-wellbore pressure drop. It seems that better quality of cement or stronger cement will reduce the near-wellbore tortuosity. So from the reservoir scale modeling, the observations are that the initial fracture permeability significantly affects propagation pressure, history, and the fluid migration or complexity of stimulated fracture network. The impermeable case of impermeable cohesive DFN with reduced aperture best matches the long-term bottom hole pressures, and in this case we observed that stimulation is a combination of localized fracture activation, and there are 4 key flow pathways which are similar to the fiber optic observation. I want to point out one more thing. In this model, most of the DFN is stochastic. So consequently, the model doesn't exactly match the field data or fiber optic data, and that's not expected. However, the model does show the same trends. So that's what I prepared for today. Thank you for your attention.
Well, thank you, Branko. Outstanding presentation. We do have a few questions. I don't know whether you can see them, but I'll start with Ashley. And he's going back to your discussion of breakdown. Do you believe that there is just one breakdown, or is it multiple? And if so, have you noticed the breaks, or are they in steps? And he's interested in this because it may have some practical ramifications.
Is there one or multiple breakdowns?
Yes.
I think they are multiple. I mean, okay, one of the models has been focused on relatively short time, and there we observed only one breakdown. But then the second model, where we looked at the effect of DFN, that model clearly indicates the multiple breakdowns. So, yeah.
Okay. The next question, I'm not quite sure who it's from, is does your model allow for bedding plane parting? If suppose you were doing a model in an unconventional reservoir, so that you could have fracture propagation in a non-principal direction, or not perpendicular to the minimum stress.
Yeah, I mean, in principle, it's the same thing as looking at the effect of the DFN. And I mean, I've shown in a couple of examples that the DFN definitely, depending on the conditions, the strength of the DFN and stress and so on, can result in arrest and diversion. So clearly, if those discontinuities are created in a model as a subhorizontal, they would have effect of bedding planes on fracture propagation. So,
and for attribution, that question was from Matt Adams with shear frac.
okay.
Then the next question is from Professor Bazant. He would like to ask something about long-term fracture growth.
Yes, excellent work, Branko. You hear me?
Thank you. Yes, I do, Professor. Yeah.
But I have doubts about this whole thing regarding long-term viability, because to make it viable, you would have to work for not months, probably years, maybe decades. And for that, you need to reach the heat source over a sufficiently large volume, so you need to propagate cracks much farther. Your times on your diagrams generally that you showed were like 300,000 seconds. That's about 4 days, or several hours. But for long term, you need to reach propagation of the system continuing farther away, and that's sufficient, have a sufficient aperture farther away to convey the heat not by conduction but by convection. At Northwestern we had a project which I was part of in 1973 on together with Los Alamos on geothermal energy, and they drilled into the caldera of Hemes caldera near Los Alamos, and it created one crack, no horizontal drilling at the time, of course, and another crack intersecting, and it gave water over 30 degrees C for a month, and then it decayed, and in 3 months it was down to under 100 degrees C. So how do you envisage that the system can grow in time? And you would have to you have to defeat the scaling of diffusion, which is the output decreases the square of the distance of penetration front. So that's a very fast decay, and the only way to defeat it is convection through cracks.
Yeah, yeah.
So that's a basic question or viability of. I mean, your work was very impressive, but it answers only doesn't answer this fundamental question.
Yeah, I mean, I'm pretty sure you know quite well the biggest challenge for any numerical model is if we had to somehow mix processes which are occurring at widely different time and length scales. So, okay, if you're looking at the effect of temperature on fracturing, which is somehow driven by heat conduction or advection. On the other hand, in the same time, we are looking at flow in a fracture occurring at much shorter time scale, which would be then dominant thing if we are looking at hydraulic fracturing driven by the fluid injection and the pressure. So those things would be challenging. I mean, so I assume your question is how would this numerical scheme deal with these with hydraulic fracturing at long time scales? I mean, so
fracturing also conveying the heat because you cannot rely on diffusion.
Yeah, so there are ways to basically implement this in a scheme where, okay, running this thing fully coupled in multiple ways and basically synchronized wouldn't be possible because the time steps from the fastest process would be incredibly small compared to the time that we want to simulate. So, but there are ways where we can basically assume certain conditions, let's say steady state flow in a fluid or equilibrium, mechanical equilibrium, and then advanced model, simulating these slower processes, and then periodically check the equilibrium and condition for fracture propagation. So yeah, we can actually simulate heat production, considering the effect of secondary stimulation and so on for the time scales of months and years. Using this kind of approach.
I'm going to have to intervene. Apologies, Professor Bazan, because we got a couple of other questions, and Branko has a hard stop at the hour. And the next question is from Luke Frash, and Luke is interested in what sort of initial conditions did you specify in the cement, the stress state, the microcracks, tensile strength, and how did that compare with the rock? What in your near perforation modeling?
Yeah, so basically okay, I think they probably can reply and provide details to Luke. I mean, we try to simulate the entire process of drilling, cementing, and so on. So the cement takes some stresses due to any deformation, subsequent to its installation or healing. So yeah.
So Fatmir is interested if you ran any simulations assuming a different stress regime than what exists likely at Forge, say strike slip. And
Yeah, no, I think these, I mean, yeah, we haven't done that. I mean, yeah, so these are basically simulations carried out for the stress in situ stresses that we believe are probably the most representative. And but we understand uncertainty with that. So
would you like to speculate on what would happen in a strike slip regime?
probably, I don't know. Probably I wouldn't.
Okay, that's a good answer. And then Carlos, please, can you explain more about the geological mechanical settings? And yeah, maybe I can help with that, Carlos. There's a huge amount of information that's available. This is characterized as a granitoid, varying from granodiorite to actually a gneiss situation in the reservoir. And the geothermal data repository, if you Google that, you find all sorts of published information on Forge. Luke, if there's time, I'll come back. Ali, when the viscosity is low, the fracture initiation will be accompanied by instability. Is the model able to predict this instability?
Would need to maybe connect it, maybe by email, or I think it's a little bit more, requires a little bit more time to discuss.
Okay. And Ajmal, how are the orientations of various fractures in the DFN considered in modeling and their effects? And I think maybe you've answered it. You've said that they were largely stochastically generated, but some of them were based on microseismicity that was measured.
Yeah. So basically, the stochastic model was created uh, uh, based on FMI logs, site characterization. So the model matches the observation of the orientation, size distribution, density, and so on. But then it was refined where we had the information based on microseismicity and so on. So there are some deterministic components, but in the limited volumes.
And then we do have time to come back to Luke. When you say aperture, do you mean pure cubic law, or i.e. mechanical and hydraulic fracture are equal? Maybe can you talk?
They are not equal. It's hydraulic aperture is not equal to mechanical. We do use cubic law, but it's hydraulic aperture. So basically, whatever aperture would give the given permeability. So yeah, it's not mechanical aperture.
Okay. Well, I know our speaker has to leave. He's got a commitment right on the hour, so we're going to give him 2 minutes to catch his breath. And I'd really like to thank him and thank everybody for participating. A really thought-provoking presentation on an interesting set of field data. So thanks very much, Branko, and we'll see everybody in a couple of weeks.
Thank you, John. Thank you, everybody, for attending. And if anybody has additional questions, need more discussion, please feel free to send me an email. So, yeah.
Okay, thanks all.
Congratulations, Branko.
Thank you, Christine.
All right, bye for now.
Thank you. Bye.
Thanks, Branko. Okay,
Thanks, John.
see ya.
Yeah.